Hello, it's Duncan. If you're playing along, you may remember that I've been threatening to introduce the reader monad for a couple of episodes now. In contrast to context receivers, which we covered last time, functions using reader monads signal that they need some context to run in their return type rather than their input types, returning a function that will be executed later rather than straight away. Instead of starting from the commit at the end of the last episode, I've backed up a bit for this one, so we aren't trying to remember how context receivers work. If you want to see a refactoring from context receivers to reader monad, well, I've recorded that as well, but most people thought it was just too much, so I'll publish it separately. This is the most advanced topic that I've covered so far, but I think it's a rewarding refactoring that helps internalize what monads can do for us. So strap in for
the code here is in a sort of parallel universe state. It's as if we'd carried on from a place in the last episode where we passed transactions into our save and load method of items, but we didn't carry on with context receivers, but instead we carried on passing transactions in, but produce this with transaction method on items that is implemented by database items by creating a transaction and invoking the block with it. And in stock, then, that means that we can run our load code here and our save code here, giving them both the transaction from items with transaction. This will probably only make sense if you've seen the previous episode on transactions and context receivers. So if you haven't, then please go and watch that first. I said in that episode that functions could communicate in three ways: their name, the parameters they took, and the parameters they return. So save, for example, is communicating what it's doing through its name. It's communicating the fact that it can fail because it's returning a result type. And it's communicating the fact that it needs a transaction by having this parameter transaction. Today we're going to ask the question, and hopefully answer it, what if save communicated that it needed a transaction not through its inputs, but through its outputs? So what would a version of save look like that communicated through its outputs? So we'd say fun save. We know it's going to save a stock list, and we know that it's got to communicate that it can fail, so it's going to return something like this result. But now I'm going to return some other wrapper, which is that it requires a transaction. And we know the type of that transaction because it's tx here. And requires transaction is going to have two types. It's going to have the type of the transaction that's required and what will be returned if you provide that transaction. So let's make that type happen, and we'll do it in here. And IntelliJ suggested T and U. I'm going to call these TX for transaction and U for the return type. Now let's go off to our tests and see how we could use this. So I'm going to create a new test, which we're going to call requires transaction. And this is going to call that method on our items. So we're going to go to items, and we're going to call save, and we're going to give it our initial stock list. Now we need to check that that is the version we've called, but it is because this one here has another parameter, so we know we're calling the right one. So having called save, let's check that it has actually been saved. I think we've got a version of this here, so we'll use the version we know is working. And we'll say having called save, we expect that when we load, we see the stock list we just saved, and this is the version of the code that requires the transaction to be passed in. We'll leave that there for now, and we'll run all the tests in here. Okay, the first problem is that we haven't provided an implementation of what that method would look like, so our subclasses aren't compiling. Let's fix that in here. What would this look like? Well, we've got a save that's implemented in each one of our subtypes. It's this one here. So let's try and use that. We know we need to return a requires transaction, and that requires transaction is going to have to call this save. So that implies that it needs some sort of block. Let's put that into here. We're going to call this f, because why not? And this function is going to be a function that requires a transaction and will return an R. And we'll make this a property. So now in here, we can pass a lambda, and that lambda is going to call our other save, passing it the stock list. And in this lambda, it is going to be a transaction of the right type. So let's just put a tx in there so we remember what it is, and we can pass it into here. Okay, let's see whether that makes everything compile. Well, it does, but now requires transaction in our test has failed. And it's failed because we didn't save anything. Now, this probably isn't surprising because all we ever did in here was remember this function. We didn't invoke it. So let's put that away down here. And I'm going to move the items that we're implementing over here so we can see both sides at once. Let's remind ourselves of the type of this. Ask IntelliJ to fill it in for us. Okay, it is this horrible requires transaction of a TX that will return a result. So this hasn't actually saved things yet. I think a better name for this is saver. So the saver is a thing that we're going to do something with later. And what are we going to do with it later? Well, if we could say saver.run in transaction, we could give it a transaction from somewhere. Where would we get one from? Well, we've got this items dot with transaction that has a transaction. So we could take this saver and run it in the transaction that came from the block. This doesn't exist yet, so let's create it. There it is over here with its transaction. And what should this do? Well, it's got a function and it can invoke it with the transaction now. So this required a transaction and this provides it. And this is going to return an R, and I suppose this might as well. So we'll say that can return R, and that R will be provided by calling that function. It's really nice and simple. So simple that we can make it look like that. And now if we run, our test pass. Now, what about load? Well, we could do the same thing. Load requires a transaction and returns a result. So we could add a version of it that was fun, load, that doesn't require a transaction, but returns a requires transaction with the error type of the other load. I'm going to move this over here for a bit so we can see all that line in its full glory. And we know we can solve the problem like we did here. So we can return a requires transaction that does a thing, and that thing is going to be the load from up here that needs a transaction that this requires transaction will provide later on. Let's just convert that to an expression body and format like that, and we'll do the same here. Okay, now we've got a load, we could use it in here. So here we could say, we could use items load without the transaction, and we could run that in a transaction that we got from this block. See whether that works. And it does. I like this saver here to remind us that we're not actually doing anything yet, but I'm going to take this type out just so we can see more of what's going on over there. Okay, so we've done saving and we've done loading. What happens if we want to update an item but in a single transaction? So let's write that in here as well. We'll do all this in a transaction, so that's items with transaction some TX. Okay, so first of all we need the loaded stock list. So that's going to be our items.load, and we're not going to call that version, we're going to call the version that requires a transaction. Then we can run that in a transaction with TX. Now then the type of this is a result of stock list. So we don't yet have a stock list. So we can then say loaded flat map to get a stock list or short circuit if there's an error. What do we want to do with this stock list? Well, we want to update it in some way. And for now, I'm just going to change its last modified. So we're going to say stock list.copy last modified is the stock list's last modified plus an hour. And this is updated. Now we want to take that updated and save it. So we're going to take updated and we're going to say items.save, the updated version. And that will be the version that requires a transaction. So we can then say run in transaction TX. Now as a result, that's going to be passed out of here and threaded all the way back through here. So I think we can probably say this is result. And having got here, we can check we've returned the right thing. Say assert equals success of updated is result. What's updated? Well, going to be the initial stock list with this same change to last modified. So I'm going to say here this is val expected, would have been a better name. So that's initial stock list, copy initial stock list. Last modified is the initial stock list's last modified plus an hour. So we can say that. Let's see whether that's true by running. Good. And then also we expect it to have been saved here as well as returned. So let's go and ask this question here. So when we go and load again, we should see the expected was saved. And it was. Okay, so we've managed to make this work, but it's hard to argue that this is understandable code. We've got these run-in transactions and flat maps and so on sprinkled around with our actual main code, which is the loading and the updating and the saving. So let's see what we can do about that. We can take this thing and make a variable out of it. And whilst IntelliJ suggests save, we know that it's not actually saving, that's a saver. It's not saving until we run in transaction. Now what I'm going to do is make this into a block of code. So I'm going to say val f is a lambda that does those things and returns the saver. And then here we can call f to get back our saver. Bear with me, but let's just check that runs the tests. And it does. And now this f here relies on this stock list. So I can't pull this out unless I give it a stock list of its own. There. And I need to tell Kotlin the type of that for now. And now this stock list here will be this one here, not this one here, but I can provide it in here. Is that all true? The test will tell us. And it is. Now why did I do that? Well, I did it so I can take this out of here. So let's do that, put it up here. And now this is effectively our updater. It takes a stock list and it returns a requires transaction that will update that stock list. So let's give that the name data and we will ask for its type, which is horrible, but the truth. We can make this slightly nicer by inlining that. Okay, that's handled part of our operation. What about this items load? I'm going to pull that out as our input. And I'm only interested in the one in here. So this is our input. But note that this input doesn't actually do anything yet. It just returns the required transaction. So we can move this out of here as well and run that. Good. Now we have an expression here that has separated out the housekeeping from what we actually want to do. So I'm going to extract a function for it. And I'm going to call this Fred because I don't know what to call it at the moment. Go and find Fred, and it would be nice if it wasn't part of this contract, so let's pick him out of here and put him in here. Unfortunately, Fred required the transaction from the items contract, but we can fix that by just saying there is some transaction Fred. Has that been successful? Yes, it has. And now we're going to generalize Fred. So the first thing is the input. We don't really care about this type and this type. So I'm going to have a type parameter for our stock list, and that's the thing we're returning, so that's I'm going to call R. And we'll replace the stock lists. And IntelliJ said this R needs to be a subtype of stock list, but in fact, we don't care about that. We get rid of that there. And while we're there, this stock list name here is just an R. So we'll rename it to R. Okay, what about this stock list loading error? Same thing. That we'll just call E. In here. And that was a subtype of our E, so we can get rid of that. And now we don't really care this is stock list loading error, so we can get rid of that and run. Now this fails to compile, and it fails to compile because our two methods, save and load, return different subtypes of stock list loading error. This returns just stock list loading error, and this returns a specific stock list loading error. It's a little bit embarrassing, but we can solve that problem by calling this one E1 and introducing an E2 that is a subtype of E1. And now our updater is allowed to return subtypes of whatever the input returned. So we'll call that E2. Is that true? We get rid of that and run. it's happy. There's another generalization we can make, which is that at the moment this updater takes an R and returns a result of R, but it need not return a result of the same type. We could add another R2 in here, and we could say that the updater takes initial R and returns R2, in which case this would be a result of R2. And we'll just rename this initial R to be R1 and run. Good. This is all a little abstract, and things are, I'm afraid, going to get worse before they get worse. Suspend disbelief though. First thing we're going to do is we're going to make this input into a receiver. And that allows us to say input, whatever this is, given a transaction, and whatever updating is. Now if we inline these things back again, and the same with our input, and fix the lambda out of the parentheses, then you see that Fred is doing the unwrapping of our result, and it's managing the run-in transaction for us. We can concentrate on just what we actually want to do, which is to load a stock list, update it, and save it. There's just one sort of symmetrical problem, which is that previously we've taken something and in the transaction block we've called run-in transaction. Here though, this code we're not calling run-in transaction on it, and that makes it difficult to compose. This thing's output is different than its input. What we'd like to do is to be able to call run-in transaction to make everything symmetric. In that case, Fred would have to return not a result, but a requires transaction, given the TX, and returning a result type. And we can make that happen just by creating a requires transaction for it. We say this equals requires transaction, given that block. And we're now not going to return from here, that's just going to be the result of the block. Is that true? Well, it passes the test, and that's a good start. Let's try and find a way to lay this out. Now we look at this. This takes a transaction here and puts it in here, but there's a transaction available on this requires transaction. So if we were to say TX there, this would be unused. So we get rid of that and run. Good. And while we're here, we don't know this is actually loaded, it's just something. So let's inline that. And finally, I don't know whether it's an updater or not, it's just some function. Okay, now let's look at this function signature. It's got one input that is this wrapper, this requires transaction around something, and it takes a function that takes the thing that was wrapping and returns another wrapper, wrapping the thing that was returned from the function. This may or may not be familiar, but if we look at flat map, for example, on our result, you'll see that this takes a result that wraps a T and takes a function that takes that T and returns the wrapped version, and this returns a wrapper. So this is in fact flat map. And this is flat map on our requires transaction, where our requires transaction is returning a result type. So I think I'm going to call it flat map result, because it's quite specific to result for K. This is result for K's result. Well, it may be specific, but it's also quite general, so we can take it, make it public, and move it over to go with our reader. It was a long time since we've been over here, but our requires transaction was actually really quite simple. There it is. And we can add to it flat map result as an extension function. Let's just run the tests. And that's good. Okay, focusing now over here, we've called this required transaction, but it doesn't in fact have anything to do particularly with transactions. So this could be any context. We could call this requires context, in which case this would be just C for context, and then this would be run in context. So we've used it to pass transactions in, but this could be anything. It could be a transaction, it could be how to get hold of a database connection, it could be our configuration, it could be our logging, it could be anything that a piece of code requires that another piece of code can supply to it. And because of that, in fact, functional programmers call this the reader monad. It's a monad because we can flat map on it, although there are other monad rules as well. When I say we can flat map on it, actually we haven't. So let's see whether we can define flat map here. So what would flat map on a plain reader look like? Well, its signature would be flat map. It would take some sort of function that takes what we have inside us, which is an R, and returns a reader, with the same C as we have and some other R2. So we would need to say there is an R2 here. And this is going to return a reader of C to R2. How's it going to do it? Well, we know it's going to return a reader, and we know a reader takes a block. Let's name this C for our context while we remember. And now we're going to call the f that's inside us, which is this dot f, with the context. And we're going to call our parameter f, given what that returns. And that we need to run in the context of C. That's all very well, but it's unused. Let's see whether we can implement this flat map result with it. First of all, let's remove this tx, or at least call it C for context, and remind ourselves here that this is not now a transaction, it's just a C. So in flat map result here, we could call the bigger flat map, and at that point we'd have an R1 result that we could pass to a reader that would take the R1 result and call result flat map to give us our R1, and on that R1 we can call f, given the R1, and run that in context. Don't need that anymore. And this just needs the it, which we will call C. Try that. Good. Returning to the contract then, if we were to pull this out into here as updater, you can see the symmetry now. We have a saver, which calls a single operation. We have load, which is a single operation. And we have a compound operation here, which takes item load and then pipes it into save. But we treat it in the same way. So once we have two readers, we can compose them with flat map and treat them like a single one. Which, if you think of it, is like we're doing with results in flat map, when we have a result and we compose it with a function that returns a result to get another result. In the last episode, though, we saw we can do essentially the same thing with context receivers. So the question is, when should we be using reader and when should we be using context receivers? And the answer is, I don't actually know. I think it's significant that the arrow functional library used to have a reader monad, and they have deprecated that now that we have context receivers. So it seems that context receivers are the way that Kotlin is going. Are there problems that the reader monad solves that context receivers don't? Again, I don't know, because I'm not really a functional programmer. I'm just a guy on YouTube that's learning about this stuff and telling you what I've learned. As with the result monad, I think there may be use in particular when we're deferring decisions, because we can build a reader, compose it with other readers, and wait until the context is actually available. Now, that may be a thing we can also do with context receivers. I don't have the experience to tell. I think Gilded Rose will go forward with the context receiver rather than the reader version of this, but if nothing else, I feel I've understood the reader monad through this process, and I hope you have too. As I've probably mentioned in the introduction by now, this is the second episode on this topic that I've recorded, the first one starting from context receivers and refactoring from there. I'm going to publish that version as well, so if you've enjoyed this or just found it useful, you might decide that that is worth watching as well. I'll give a link to the episode in the notes, or you can find it by subscribing to the channel. I should say that this foray into understanding the reader monad was inspired by Uberto Barbini's forthcoming book, From Objects to Functions, which is published by Pragmatic Press, and I'll provide a link to that. And whilst you should buy that book, you should first of all buy the book that I wrote in that price, called Java to Kotlin, a Refactoring Guidebook, details of which are in the show notes below. Thanks for watching.